So there was a lot of discussion in one of our most recent checks around confusion of what Elasticsearch is doing and how it works. So I kind of interpreted that two ways. One is like, how does Elasticsearch specifically work, and how does its DSL work, which is useful. I will not be talking about that today. The other useful bit, I think, though, is what problem is it trying to solve and how is it solving that problem. So in order to do that, I thought we would kind of build our own IR system, so our own information retrieval system. So let me share my screen so I can show what I put together as a little stub for us. Can you see my cursor if I type? Yes, okay, perfect. So I have here just a simple directory with a couple files that we'll talk about in a second, and this directory of text files. And this is the IR problem, right? This is the definition, right? You have some collection of documents that you want to be able to index and search over quickly. And so these are our example documents, right? This is the cat in the hat in document 1. The cat sat on the mat in document 2. And the rain in Spain stays mainly in the plain in document 3. So how do we store those in such a way that we can very quickly search over them and find relevant documents? So if I were to ask you, here, take this book, look at a book, find all references to snow machines. How would you do that? What pages do snow machines appear on?
Look in the index.
You look in the index, right? Yeah, you go to the back of the book and you pull up this index and you're like, all right, S, snow machines, pages 20 and 149. And then you can flip right to those pages. The alternative, right, is flipping through and reading the entire book and keeping track of where all the references come from, which is pretty expensive to do and infeasible in a fast search. So like ours, right, we can't read over the transcripts or descriptions and titles of every single course every time a user puts in a query. Instead, we create an index. Does that make sense to everyone? What the strategy here is? Cool. So that's exactly what we're going to do. And we'll do it just in raw Python. So if you have the code, you can follow along. You don't need to pip install anything because there aren't any external packages that we'll be using. So I have two files here. One in which we'll create the index that we just described, and another that just creates the index, and then it'll allow us to display its contents, it'll allow us to query it, and this is typically referred to as an ingester. So I've described what the data structure of an index looks like here. This is what an index is. It is a dictionary that maps terms to the documents that have that term. This is why it's called an inverted index, because you're not indexing documents, you are indexing the terms to the documents. So here's an example. We might go over a corpus and we say, quick, this appears in document 1 and it appears in document 3. Brown appears in document 2. Fox appears in document 1, document 2, and document 3. And that's exactly what you saw in the other index at the back of the book. We also keep track of one extra bit of information here, which is the number of times that that term appeared in that document. And why is this useful information to keep track of?
It's probably more relevant if it shows up more times.
Exactly, yeah, perfect. So here, right, Fox is probably as equally relevant to documents 1, 2, and 3 But here, quick is probably more relevant to document 1 than it is to document 3. So if you're going to be building a search algorithm that returns a ranked list of documents given a query, this count, this term frequency, will allow you to rank those results. And so that's what we're trying to do in search. That's what we're trying to do in Elasticsearch. All right, so let's go ahead and see if we can build this. Let's just say self.index here is a default dict of, and is there anyone who doesn't know the collections library in Python? Because we'll be using counter and default dict here. If you haven't, I recommend you check out the documentation. It's a really cool built-in that is very useful in text processing and keeping track of stuff. So what this is saying is, this is an index. It is a dictionary of lists, and it has some nice properties associated with it that we'll use. All right, so the first step then is to fill up our index. So how do we do that? We'll take a file in. It'll be one of these files, right? And it will have to read in each line, and it will have to index that term into our inverted index, right? So what we can do is we can grab the name of the document, and I'm just copy pasting code in from my repo. So this is saying get the document name. So this will be document 1, document 2, document 3, and then let's say, okay, we're indexing it. And then we want to keep track of how many times each term appears in this document. So we want to go through this. We want to say the is once, cat is once, in is once, the is now 2, hat is 1. And then once we have all of those, we can add an entry to the index. So let's go ahead and do that. And if at any point you have any questions, just speak up and let me know. So we'll make a counter. This is another cool collections item. A counter is also a dictionary. It is a dictionary of some type to an integer. And it's useful because it also has some nice default behavior built into it. So like a default dict, for example, will allow you to do plus equals to something that is not in the dictionary, and it will create it. Same thing with counter. And so we'll use that in a second here. So we're going to go over each line in our file. And we'll say for each term in that line, and we do a strip to get rid of characters on the left and the right, including the new line. And then we do a split. And what split does is it breaks on any white space character. So this will give you a list of tokens now. So this will give you the cat, or sat on, or the mat. So this gives us all of our terms. And then we can say term counts of that term plus equals 1. And we can do that because of our nice default dict.
Jump in real quick.
Yep.
If you wanted to, you could replace lines, or this I think is the answer, but just want to verify that you could replace lines 27 and 28 with calls to 2 different methods. One method that would split the tokens up because you're assuming that that split method would do it on white space, and then you could do you could process each term individually besides just making a counter with them. But for simplicity's sake, we will skip those 2 steps. But those are going right here.
Yeah, exactly. And this is a good point of one of the simplifications that we're making is we assume that all this text has been pre-processed in some useful way. So for example, in these files, you see that we don't have any capitalization. It's all lowercase text. We don't have any punctuation. And all of our tokens are separated on a space. And so if this was something that you wanted to expand upon, then having a text preprocessor would be something else that you'd want to write. But it could be something just as simple as strip out all punctuation and lowercase. Or it could be as fancy as building up a language model and doing true casing and BPE and all kinds of fancy stuff. Does the text preprocessing step make sense to people? Okay, awesome. So now we have all of our terms in this document. We have a count of all of them. So this term counts will have the, cat, in, and hat in it, and it'll have 2 for the and 1 for all the rest. So now that we have those counts, we're just going to go ahead and we are going to add to our index. So we'll say for term count in counts dot most common, which is a method on our counter that just returns all of our terms and counts in the order of count. And we'll say self dot index of our term, right? This is our dictionary now. This we will say append a new tuple of doc name and count. And that's it. That's how you index a document into your index.
Real
So
quick.
all of this makes sense. Yeah.
Default dict would say that when a term does not exist in your index on 30, that will just make it a list.
Yeah.
Okay, cool.
Yep. Because we've said this is a dictionary of lists to the default dict, this will say if this doesn't exist in there, this term doesn't exist in there, it will create a new entry that goes from that term to an empty list. And then you append it here.
Rich, is there a particular reason we're doing the sorted term addition rather than just iterating over the keys unsorted?
Nope, it doesn't matter. So this could be dot items. Cool. So cool, we index a document. How do we index a directory of documents?
For loop.
Index every document in the
Yeah, you write a for loop. So a file name in os.listdir, given the directory, we're going to say if it doesn't end with .txt, we're just going to skip it. I'm just copy pasting that in. This is so you can put other things in there like a .md file, or your .ds store if you're on a Mac isn't going to mess it up. So we're only interested in the text files. And then we'll say file path is equal to os.path.join. Given the directory, file name, and we'll say self.index document. Cool. Does that all make sense? Pretty easy. Another thing we can do is we can just keep track of how many we index. That way we can print it out and make sure that it's what we expect.
Your variable name has an ed 141. You should remove.
Num indexed. Cool. So that should just keep a counter. And every time we index a document, we increment it. And then at the end, we print out how many we index. Cool. We're almost done building our indexer. So our ingester over here on the left, this we're going to pass in this directory that we want to index, this corpus directory, and we will call index directory on it, and then we'll display it. So I wrote a little pretty print method here just to make it easy to see what's in there. So this is just saying loop over everything in our index and then print out the term and the document. So let's give it a shot. So we can say Python ingest.py help data in. So we'll say, okay, corpus, what happens? Mixing one required positional argument directory. So where do we mess up? Index.index directory. We need to give it the actual directory. So args.data in. Okay, cool. So this is what we saw. We ran python ingest.py. We gave it our directory of documents. It stepped through, it indexed each one. It skipped the one we weren't interested in. We indexed 3 documents total. And this is what it looks like. So is this right? Cat appears in document 1 once and document 2 once. That looks good. Hat just appears in document 1. In is in documents 1 and 3. Yeah. Does everyone see what we did? Any questions? Cool. Now this is like the back of a book, right? And so if I'm interested in what are all the documents that have cat in them, then we can just query this thing and we'll know very quickly. Now, just looking at the back of a book, right, that'll tell you where to look. But we have this extra piece of information here, which is how many times does it appear in that document. And like Justin said, this is useful information because we want to be able to rank our results. And so we want to return the ones that reference those items more frequently. So how do we do that? We want to write some kind of method here that allows us to query our index now that takes some term and returns a score. Let's call this query TF IDF. Now, TF IDF is a scoring algorithm that does exactly what we want it to do. This is saying, show us all the documents, and documents that have the term more frequently are more important. That's the TF part. Now, there's another bit that the IDF gets us. IDF stands for inverse document frequency. What this is saying is that terms that appear in many documents likely carry less information than terms that appear in very few documents. Why does that make sense? Or why could that make sense?
Is that like filler words, kind of?
Like what words?
Like filler words, like if you had like the and everything.
Right, yeah. Filler words like syntactic glue. We also call them stop words, right? They're just words that hold the language together really and don't actually convey a lot of meaning. So the idea is you might have a multi-term query and we're just gonna sum up the TF IDF scores for each term. And we want the filler words to count for less, right? Just because this has the in it a couple times doesn't mean that it's actually, you know, the is most relevant to this document, for example. All right, so let's score all of our documents. We're just going to say doc scores. We'll make it a default dict to floats. So this will map our documents to their scores. And for each term in our query, And we'll do the same kind of text processing on this. So this is saying we can pass in full query, let's say, and this can be multi-word. So this could be the cat or rain in Spain. And so what we do is we strip out stuff on the sides and we spell in white space. And then we'll say for doc term frequency in self.index term, doc scores of that doc plus equals this TF-IDF score. So that's literally the term frequency, that number that we have here, times whatever this IDF thing is. And then you return those items sorted. So let's do this for now, and let's see if we can solve this bit. This is something that, honestly, you can just look up on Wikipedia. It's not that complicated, so, in fact, though, so we can step through it. So this is going to be something that takes a single term, returns a number, and this is what it's going to look like. So it is the negative log of the number of documents in which the term appears divided by the total number of documents. And so as this term appears in more and more documents relative to the total number of documents, this number will go down. And so we'll multiply our score by a smaller and smaller number. And you can kind of see exactly what that's doing, right? This is the number of documents that the term appears in. This is the number of documents. So as this goes up, this whole thing goes up. It goes to 1. And then the way that negative log works is between 0 and 1, which is the only place it can be, right? Because this is going to be anywhere between 0 and the number of documents. It goes to positive infinity as x goes to 0, and it goes to 0 when it's at 1. I don't know if you can visualize that. We can probably take a look. So if I do negative log of x, zoom out here, yeah. So you can see we're interested in the area between 0 and 1. It goes to positive infinity when it's at 0, and at 1, it goes to 0. So that's all that's doing. Any questions up to this point? Cool. So let's see if we can query it. Let's say, while true, we'll grab a query. And then we'll say result equals index dot query TF IDF of the query. Cool. Let's see what that gives us. I don't actually know. All right, so there's our index, and we can query for stuff now.
You'll probably want a print statement as well.
Probably want a print statement. Probably. So what are we querying for?
Cat.
Cat. Index object has no attribute numdocs. Okay. So here we're keeping track of the number of documents, right? We need to know that for IDF. This failed because we don't actually know this right now. But we can get that information, right? We can go over here and say, all right, for every document that we index, we want to say self.numdocs plus equals 1. Let's do that. Self.numdocs equals 0. And then here at the end, we'll say self.numdocs plus equals 1. Now we have this. So this goes to show you that your index has this structure, but it can also contain other meta information that could be useful. Here is just the number of documents that are indexed in total. And that allows us to calculate the IDF. So let's try this again. Query, cat. All right, cool. So here we see, this is our result. We have a dictionary with 2 items, document 1, which has this score, 0.405, and document 2, which has a score of 0.405. Cool. So why are those scores the same?
Because it occurs maybe once in each document.
Yep, exactly. So cat appears once in document 1 and once in document 2. So they'll get the same score. What if we do the word in? So here we see document 1 scores 0.405 and document 3 is twice that, because in appears in document 3 twice as many times. And there you go, Elasticsearch. That's all it's doing. It's just doing something like this, right? You index your documents, you have a way to very quickly search over them. And then from there, it's a matter of making improvements. So one of the things that we talked about, for example, right, is having some kind of pre-processing on your text. And that includes casing, that includes punctuation, that includes things like synonyms. We won't talk about all of those. What I do want to talk about, though, is BM25. Now, when you learn about information retrieval, TF-IDF is the standard way to explain it. But what has been the industry standard for doing token search for decades now is this algorithm called BM25, which is very much like TF-IDF, but there's a slight modification made to it. And that is, it takes into consideration the size of the document. So you can imagine if you had this 200-word article that talked about cats in 10 different places versus a book that is, 800 pages long that also talks about cats 10 times. The idea is that the article is probably more relevant to cats than the book is, right? And this, TF-IDF, won't know the difference. It'll say they're equally as relevant. So to get around that, what we do is we're going to also keep track of how long each document was that we indexed, and then we'll correct for that. So let's see how we would do that. What I've set is, let's keep track of all of our document lengths. This will be a dictionary that goes from the document to how many tokens are in it. At which point we can say that, let's say numdocs, numdocs just returns the length of this. And then when we index a document, instead of doing this plus equals 1, what we'll say is doc lengths for this document is equal to the sum of our term counts dot values. So if you remember, this term counts is a mapping from each term of the document to the number of times it appears. So if you sum up all of those values in that dictionary, that gives you the total number of tokens in the total document. And so we'll say the doc length of that document is equal to that sum there. Okay, cool. So what else is there to do? Well, we actually need to make our new BM25 algorithm. So let's write that down here. Query BM25 self query. It's going to be the same thing, really. It's honestly going to have a very similar structure to this. So let's just copy this. We're going to do the same exact thing here, except this TF IDF is going to change to TF times IDF times some document length normalizer. And that's the only difference. So it's just a matter of saying, what is that document length normalizer? What I did to get this was I went to Wikipedia and I looked up BM25. And it's this right here. So let me call this. There are a couple of constants in here. Let's add those in here that allow you to tweak the behavior of BM25. So we'll say K1 is a float. Because you want to specify how quickly do you stop caring about a term as the size increases, right? And those two constants allow you to kind of tweak how much you care. So we don't have to fully understand exactly everything that this is doing, but you can kind of see, okay, as the length of the document increases over the average length of the document, so relative to other documents, as it gets bigger, this will get smaller. And so this will be smaller for larger documents. That's essentially what it's doing. And I have this average doc length, which BM25 needs. And so we can calculate that. That's just, oops. All of the doc lengths summed up divided by the number of documents. So that's the average document length. And that's BM25. Let's see if that works. We're still using TF-IDF. Let's say BM25. Okay. So we can query for cat again. And here we go. Look, we see that we have two different scores here. We have 0.46 for document 1 and 0.42 for document 2. Why is that?
Less terms in doc 2. Or
There
doc
are,
1.
there are fewer terms in document 1, right? So we believe that cat is more relevant to this document than to this document because this is a shorter document and cat appears just as many times. What do you think would happen if I put in the? Any guesses?
Last doc first.
They're all 0.
Yeah.
Why are they all 0?
Math.
Math. Yes. Good job, Travis. You win.
You just hand wave, it's all really easy.
Anyone? Why are these all 0?
Is it because it occurs in all of them?
Exactly. Yeah. This term appears in every document. And so by this IDF, we're saying that this term carries 0 information. Because it's in every document, right? This will go to 1, which means this goes to 0. And then we say for that term, it's worth 0. But, you know, oops, it can still be part of a query, right? And this is useful, right? So I say the cat, and we have the sum of the scores of the and cat. And the just carries no information here, but cat carries all the information. Cool. So that's it. And I show you these, like, this is how you do TF-IDF, this is how you do BM25, because you can imagine scoring these documents in any way that your creativity suits you or the problem needs, right? You could just use term frequency if that's all you cared about. So you could give document 1 a score of 1 and document 2 a score of 1 for cat. Easy as that. You could also imagine, give me all the documents that you know, score a non-zero score on all of the terms that I give it. So if I say right here, the query is cats, what's a good, document, cat document. Let's do cat document. Cat document, currently, this is what we get. We get the same 0.46 and 0.42 as we did when we just queried cat. Maybe this is the behavior that you want in your system. Maybe, though, you'll say, actually, I only want things that specify and talk about both cats and documents, right? So it may not just be a floating point score that you give it, but you might put logical operators on it as well. So you can say, give me anything with cat or document, give me anything with cat and document. If there are 3 terms, say, we could write a function that returns everything that matches on at least 2 of the 3 tokens, right? And so you can imagine writing these up pretty easily, like a method like this. And so as you start to see all the different ways you can possibly combine these together to create more and more complex searches, you start getting the Elasticsearch DSL, right? It is something that allows you to do that. You can specify, I want the TF-IDF on this field, I want the BM25 on this field, and I want you to return everything that gives a non-zero score on some percentage of the tokens. Or I want you to look at these fields in a certain way, and I want you to look at this other field in this other way, and combine them in a special way, and then return that score. And so Elasticsearch specifies this domain-specific language so that you can construct those things. This is at the heart of what it's doing. It also provides nice things like distributed clustering, right? And make sure that the clusters are, and that it's highly performant. But underneath the hood, this is all it's doing. It's creating this inverted index. It's maybe keeping track of some meta information so that it can calculate these scores, and that's all it's doing. So congratulations, you made a document indexer. You wrote Elasticsearch. Any questions?
I have a question about Elasticsearch and how it indexes stuff. So right now, the way that we wrote this, it's basically re-indexing all the documents in the directory every time we run it, right? But that doesn't sound like it would be optimal to re-index all of your documents every single time you wanted to run it. With Elasticsearch, would you point it specifically at a document to index and then say, use it, or will it? Yeah, like I guess how does it know what to index?
Yeah, so just like we have this like index document method, you can do the same thing with Elasticsearch, which is, so let's index this directory, and then we'll say index document, right? Some other doc, and then it will add it. Another thing you can do that's pretty easy is you can save this index that you've made out to a file. So maybe you have something like this. So, right, you just save it to file, which is like dump the index and doc lengths, and then you can load the thing from file, and it does the same thing. At which point you can then continue to index documents, you can continue to query it. And then what Elasticsearch does is it just has these things easily accessible. They're not quite in memory, but they are on disk and very easily retrievable.
Okay.
Does that answer your question?
Cool.
Any other questions around document indexing or information retrieval? Or like things that you don't fully understand yet?
How much more, this might be a bit of a question. It is a bit of a question. How much more work do you think it would take to get even like the most minimal search engine built with pure Python that like maybe takes in a title and a description, I guess, and an ID, and natural crap that people have written and not like a nice formatted text document, and get it to return results?
So
not like good results, but just results.
What are the missing pieces there? It sounds like the text preprocessing is one. And is there another part that you're interested in?
Maybe not, because then you just need like a little Flask server tied into this function that takes a query from the front end and then can respond with the results of query BM25. Maybe you go and grab the rest of the data out of Postgres, so you wouldn't really have to do too much indexing and things.
Really, a lot of this comes down to just baked in features, domain-specific language for querying, parsing, performance. There's a lot of that underneath is just the sheer size of the feature set that's built in, between anything Elastic adds for managing its own servers, data replication, anything for Lucene itself. That's a lot of what we're getting for a very large project for an engine. It doesn't have to be that big, because you can also look at something like Lunar, which, with its oddly named project, it's entirely client side. It's just JavaScript, and it lives in the client's browser. It doesn't have to be big.
I mean, it stores the documents in the browser too?
Yeah, for whatever small set of documents that it would need. Mm-hmm.
Interesting.
Obviously, same as putting TensorFlow in your browser, there is an upper limit to how useful it can possibly be. But yeah, there's a lot of these things are deceptively simple, and it's the other pieces about making it more robust that are what adds so much complexity to it. If you just have something that's really opinionated and tiny and you don't need to worry about performance or replication or anything.
Yeah. So
no one's winning a Nobel for this.
If I wanted to write a search engine for like a personal project, where I probably wanted something a little bit better than doing string like other string in Postgres, like this would be it.
There you go.
Yeah.
Cool.
We have 2 minutes left.
We have what?
We have 2 minutes.
2 minutes. Okay. Anyone else have questions? So it feels like then. Oh, Patrick?
Oh, never mind. Go ahead.
I mean, I always struggle with, like, I read a book on low level to high level, and it's like I understand logic gates and I understand how to build a UI, but everything in between is like lost on me. So it's really just a continuing on what Ted had said. Like, it's just more features. Like, if you don't really give a crap how relevant the top few results are, like, this could be a sufficiently good search engine for some websites. And then you can get the full scale of everything in between.
Yeah.
Kind of.
I mentioned that you can make it as simple as just the term frequency being your score. You could make it just as simple as, does the term appear in the document at all? So just like, given this term, what are all the documents? Just return them all, right? It could be as simple as that.
And then you could process images if you wanted an image search engine. PDFs. You can have some like text processing for PDFs, OCR policies.
Absolutely.
Very cool.
Yeah, it's just all layers of abstraction.
Great presentation. Thank you.
We were trying to, I just wanted to clarify this block a bit because I know it can sometimes appear like magic, but it's actually pretty straightforward.
The only wisdom I will leave you with on there is PDFs are a can of worms, so have fun.
Yeah, but they have libraries for PDF, so just use the OCR in the library and then you're kind of there.
Yeah, depends on what you need to get from them, but yeah, I'll
Not writing an OCR for PDFs. No, thank you, sir.
No, nor do you want to parse them and hope that there's a meaningful tree of any data to find something that even appears on every page. Just don't. You're going to have a bad time.
Search is actually substantially easier.
Yes.
Nobody's up for next time? Does anyone have anything?